Hello and welcome back into contour integration. I've lost track on which lecture I'm on at the moment. Today we're going to be doing this integral, which is the integral from 0 to infinity, x to the power of a minus 1 over x plus 1. And the answer that we ought to get is pi over sine pi a. It looks quite straightforward until we notice that in fact the a minus 1 is not an integer power, it's not something nice necessarily, it's quite arbitrary, and it's actually a number between 0 and 1, which makes this a random fractional power. Why want to do this particular integral? I mean, what possesses us to come up with something as bizarre as this? Well, the answer is this particular type of integral comes a lot in higher level maths. I've come across in Fourier transform, and this particular formula, for example, for those who have seen the gamma function, the gamma of x, gamma of 1 minus x, which is of course pi over sine pi x. In order to prove this formula, you actually need this particular result. So is it an easy result to prove? The first time you do it or you see it, it's actually quite lengthy and quite tough. Once you've done a lot of contour integration, particularly with a lot of estimations, branch points and branch cuts, which I will talk about it shortly, is actually not as bad. Okay, so first of all, let's get going. We're going to start with a complex integral around some complex path gamma, which we're going to see in a minute. We're going to define it in a minute. And f of z is just this thing here written in z. So z to the a minus 1 over z plus 1 dz. Okay, and the next thing we need to think is about, okay, what gamma shall we use for something like this? We need to make a few observations for this particular one. The first and most important one is fractional powers. And although we don't have logs here, fractional powers and logs, these are the common things that do come up often in this type of work. Then we need to think about branch points and branch cuts. And what are these things? I'm not going to give a course in analysis. I just want to tell you a few things so you can kind of have an idea intuitively at least. Because of the fractional powers and the logs, they're multivalued functions, so we don't have that kind of uniqueness. We create some kind of uniqueness by cutting the plane. So first of all, a branch point, whenever we have a fractional power, just so I can just put a few examples so we get an idea. If we have z to the power of a third, for example, okay, we have a branch point because we have a fractional power at z is equal to 0. If we have the log of z, we have a branch point again at 0 when we have logs. Like a 6 in there, at z is equal to 0. Doesn't need to be at the origin always. Usually they're at the origin, but it could be anywhere really. So if you had, for example, in somewhere in your integrand, the square root of z minus 1, then you'll have a branch point at z is equal to 1. So when you're having a branch point, so this is like the complex plane somewhere on my board. So this is now not necessarily the origin, but often it will be at the origin. Let's actually put some axes very, very quickly. We'll rub them off. This is now our branch point. We need to cut the plane with what is known as a branch cut, and often indicated with as a half line, starting from your branch point and moving away from your branch point to infinity, indicated by this curly line. I'm going to improvise. I don't know, I have got scissors there actually, yep. So if you imagine this is your complex plane, and let's say we got a branch point somewhere here, okay, what we're doing basically to create some kind of uniqueness is we're actually making a cut. The cut doesn't need to be anywhere in particular, somewhere that starts from your branch point and it extends forever to infinity. So this is now the branch cut from your branch point. What does that actually allows us to do? I don't know if it's going to show as a cross section, and it's not going to be very, very good, but if you can imagine now, it's like a spiral staircase. So if you're going around this branch point like this, okay, you cannot go back to where you started. This cut now prevents you from doing that. So we have kind of like, if you want, a one-to-one function. So the branch cuts normally in most work, they're taken to be usually along the coordinate axis, although many times when we just need a branch cut but it doesn't interfere with the rest of the work, we take it in any arbitrary direction. I'm going to do some examples, or maybe I already filmed some examples, I don't quite remember, where the branch cut is just taken arbitrarily. So let me just draw now up here for our problem a set of axes, and let's talk about our branch point, about contour, about branch cut, and so on. So this is the branch point. Why is that? Is because when z is equal to 0 here, we have a fractional power. So the origin, I'm going to tread on this cable, so let's move it out of the way. This is now our branch point, where we're going to take our branch cut for this particular one. Quite clearly, our integral is going to come from the real axis because of the 0 to infinity, from the limits. And of course, it's sensible, and it's because for this particular integral, I've seen it before, and this is the standard kind of branch cut we'll take for something like that. I cannot take the branch cut arbitrarily here. I have also a pole on the negative section, because of course I have a simple pole at -1, so I cannot go on the negative axis there. So the contour that I'm going to use is what is known as a keyhole contour, and it looks a little bit like that. We've got a very small circle or some kind of indentation of radius epsilon around the origin. Then we got a straight line segment just underneath the branch cut and a similar one above it. And then we got a bigger circle going round and joining everything together. So that's our gamma for this particular problem. Okay, it needs to run obviously in an anti-clockwise direction as per usual. So this at the bottom segment is going to be going right to left. It's going to be going clockwise on the inner circle, but overall the gamma is of course anti-clockwise. And then away from the origin, I don't have room to put real and imaginary. I'm going to call it x and y here. So this is now our curve, and it's probably worth labeling a little bit our bits. So this is our gamma 1, so that's the circle, the outer circle, and this is our gamma 2. And let's mark the radii. So the small circle is epsilon radius, outer circle r, and now it's sufficiently large to include of course the pole at -1. And let's also write on the top for reference, probably a good idea. So this is now our gamma, and this is our integral. Next step, quite clearly the residue theorem. It's a good idea to say, okay, this is going to be of course equal to 2 pi I times the sum of the residues which are inside my gamma. So not many poles there, quite clearly just the only one. So let's compute the residue. So a residue of my f of z is of course here. I'm not going to write it. F at -1. It's a bit bizarre here. At -1 is with the standard formula, limit as z tends to -1. The formula z plus 1 times your f of z, and your f of z is of course in there in the integrand, so it's z to the a -1 over z plus 1. Okay, the z plus 1s will cancel, and when we put in -1 in there, we're going to get -1 to the power of a -1. I'll probably write it a little bit differently, because this is I don't like the look of that. It's not very nice. The -1 I'm going to write it as e to the I pi, and then a to the -1. So this will now become e to the I pi bracket a -1. So by the residue theorem, if I integrate this complex function around the keyhole contour that I've got up there, the answer will be 2 pi I times this. Okay, so let's write it down. E to the I pi a -1. Okay. Next step. Well, the idea is, I know this will somehow come from this sections here, this straight line segments, once I let epsilon go to 0 and r go to infinity. So I probably will need to show at some point that the contributions around gamma 1 and around gamma 2, or it will be 0. So the standard thing is to integrate section by section and say, okay, I can say the following. I'm going to put the curly bracket here. So the integral around gamma 1, is gamma 1 the big one? Yeah, gamma 1 plus the integral along the straight line segment. So I'm starting from here, going all the way around. So that's now from r to epsilon. From r to epsilon. I was about to write e there. Dropped my cloth as well. R to epsilon plus the integral around gamma 2. Plus the integral along the straight line segment. Now I went from r to epsilon, now I'm going from epsilon to r, just checking that I've written it correctly. So that's that to that, yeah, so correct. Close curly bracket of f of z dz, where of course my f of z is this thing here. The answer to that is of course this quantity here, which I'm not writing because I'm going to go too far into my board. And the plans, of course, to show that the contribution of that is nothing, and the contribution of that is nothing as epsilon goes to 0 and as r goes to infinity, and then this will become infinities and zeros. Somehow put them together and come up with this particular answer from this quantity here. All right, so now the real work starts, and this is actually what makes this particular question long, is these estimations around gamma 1 and gamma 2. I'm going to go in some detail. So this is now what we are going to do. We're starting with the integral around gamma 1 of f of z dz modded. We need the parameterization of gamma 1. Gamma 1 is the big circle. Gamma 1 z is equal to radius e to the I theta dz ir e to the I theta d theta, and the limits for theta will be from 0 to 2 pi going in that direction. So 0 to 2 pi. So this is now the parameterization of gamma 1. So that is equal to modulus 0 to 2 pi. And now my f of z, putting now my z to the a minus 1, where z is this, so don't know where to stand so we can all see what I'm doing. So that is r e to the I theta all to the power of a minus 1, and at the bottom I've got z plus 1, so that's r e to the I theta plus 1, and my dz is I r e to the I theta d theta close mod. Okay, bit of a tidy perhaps. So modulus, I'll explain a little bit about the modulus later on. I might have explained already in previous lectures. I don't quite remember what because I don't actually upload in the order that I record, so it's a little bit annoying. So I don't even remember if I mentioned it, and maybe I'm becoming repetitive with all of this. So it's 0 to 2 pi. Let's put this on the numerator. We've got the I from there. We got the r to the a minus 1 from this. I've got another r. I'll put them together on the next line. I've got the e to the I theta, and I've got this exponential. I could put the exponentials together as well, but I know what I'm going to do next, so I don't have to put them together. It's actually better to leave them alone as they are. So that's the numerator. I hope I haven't missed anything. R e to the I theta plus 1 and my d theta, close mod. So this is now what I'm actually doing. I'm starting with the modulus of a definite integral. I'm going to do it in real first of all. Up here I'm going to write something. If you're having a definite integral from a to b of an f of x dx, and you take the modulus of that, it can easily be proven, I'm not showing it here, that this is less or equal to the modulus of its integrand, the same integral, but now the mod is around the f of x. All it says is that the modulus of a definite integral is less or equal to the definite integral of the modulus of its integrand. And with the complexes, it's pretty much the same, although there's a little bit of a snag, and I don't want to complicate things. If we're having now an f of z, it doesn't matter if we've got a gamma or an a to b or epsilon to r or whatever we have in here. But if we're having an f of z, dz, okay, and then we try to move the mods inside, we have to be a bit careful, and that's why I don't want to open a can of worms now. It's actually equal to this f of z dz. And what is that dz in the mod? What does that mean? Well, it's actually the length of the curve. If you're having a 1 in there, let's say you had, forget about the inequality, a to b 1 dz in a mod, this is actually the length along AB, if it's a straight line segment or some curve or whatever. If it was a gamma there, that represents this integral, the length of gamma. But here we're parameterized, so it works very much like the real thing. So this is a standard inequality, and I'm going to brush it under the carpet, and I'm not going to talk about it too much because this is now goes to too pure, and I'm not qualified to discuss very pure stuff. So this is now the line that I've got, and all I'm going to say next, this is less or equal to 0 to 2 pi, and I'm going to move now this moduli from the outside the integral inside the integrand. And of course, this is the inequality that it produces. I'm going to put the r's together now. So this is r to the a, e to the I theta, e to the I theta a minus 1 over r e to the I theta plus 1, close the mod, and this is the d theta at the end. It's like the real, now it's not mod d theta, it's been parameterized. Okay, so what I'm going to do next is I'm going to use some facts about the modulus. I'm going to write them here. Perhaps it's an overkill. You should obviously know all these facts. For real complexes, z over w is of course the mod of z over the mod of w, and similarly the mod of z times w, real complex again, is the same as the mod of z times the mod of w. So I'm going to do it here. I'm not going to keep rubbing off. So we have the moduli on a fraction like this, so we can actually, I'm going to use red pen, I can actually do that separate on the top and separate on the bottom. So that's using this result here, which is fairly obvious, I like to think. And then if we have loads of quantities multiplied inside a modulus, I can take separate moduli. So I can actually say on the numerator, I can do this. Can just about fit there the moduli, something like that. I cannot do it here because of the plus, okay? So z plus w, we're going to sort of triangle inequalities. It is not equal. Okay, so what will happen now when I do this particular simplification? Let's make some room on the top to write it. A lot of things will simplify now from this particular line, and we need to see what we can do and what we're getting. It's no longer equal because somewhere along the chain of these workings this appeared, so I'm gonna have to write here this is less or equal as a consequence, and this is going to be now the following. Integral 0 to 2 pi. The modulus of I is of course 1. R to the a, this is a positive number, the r, and therefore this will be a positive quantity. We don't actually need a modulus around the a, around the r to the a, beg your pardon. Okay, what about these two things here, e to the I theta and e to the I theta bracket a minus 1? I claim both of them are 1, so I'm going to throw them away, and I'm going to justify this step in a second. Let me just write it first. In the bottom is of course r e to the I theta plus 1 and the d theta at the end. So I just want to explain, of course, why these things here are 1 if you haven't seen them before. They appear quite a lot in this type of work, and once you've done it once or twice, then it's just tedious to explain exactly the same thing. I'm sorry, I'm going to write a little bit sloppily. I'm known for writing things in a bizarre way sometimes. I'm going to say, okay, what's this? E to the I something real. Okay, some real quantity. All right, if I take the modulus of that, I claim the answer is 1, because if you think about this particular expression, that is, if I write in sines and cosines, that is the cos of real, whatever was up there, plus I sine of real, where the real, of course, exactly the same thing, the same argument, of course, close mod. And what is that? Well, that is, of course, by definition, cos squared plus sine squared, and all square rooted. It's irrelevant as long as the same thing in there. The answer, of course, will be equal to 1, with nothing else to say. This appears very, very often, and the very nice things when we're getting e to the I real somewhere in this kind of work, because we can safely say this is a 1. So this is what I've done here, because of course theta is real. Theta times, of course, a minus 1 is another real quantity, so all of that is real, so it's safely a 1. Okay, so we are on this particular line. And this comes now a very important result in this estimation, which also appears very, very often. A lot of the results in this kind of work are fairly repetitive, and although they look daunting in this particular lecture, if you keep doing questions like this, they're always the same. They keep coming up. And this is now one of the triangle inequalities, part of the same family. And if I want to be honest with you, I've forgotten how to prove it. I have to look it up, but I'm not going to prove you the inequality here. It says the following. It says the modulus, let's write z first. I don't know, I like to do things in a particular way. I don't like w before z, although alphabetically it is before. The modulus of z plus w is greater or equal, okay, to the mod of z minus the mod of w, or the other way around. I mean, I'm writing it here perhaps poorly, because you might say, okay, this is always positive, and this could be positive or negative. That's not the problem, but it's what I'm going to do next, okay? Because what I would like to do there is, of course, to say, if I flip it, 1 over z plus w modded is less or equal to 1 over the mod of z minus the mod of w. And in order to do that, they must have, of course, the same sign. There can't be different signs, and therefore I have to have this being bigger than that. So this, you can actually say z, the mod of z plus w is definitely bigger than that. It will be definitely bigger than that as well. Okay, so if you write it the other way around, it's the same thing if we swap those. And often we're writing this as the mod of z plus w is actually greater or equal to the whole thing modded, to include the both cases. So normally when you're writing it like this, okay, it should really, we can't put mods there if you want, but it hardly matters. So whatever is bigger, if it bothers you, in the estimation actually it doesn't really matter, okay? You can write it the other way around. It hardly matters. The pluses or minuses there do not matter. So we can always swap them to make sure the inequality holds. So if that's confusing you, please ignore what I just said. And I'm going to write up here, the z plus w modded is greater or equal to z, mod of z minus the mod of w, and therefore 1 over z plus w. When I turn it upside down, it flips the inequality, and of course this is now true. Okay, so this is now what we've got, and I'm going to put in a box because I'll probably need it for the next estimation. Very important result, this one. It works, of course, with 3. If you have 3 items, you can generalize it with 3 or more. I wrote it there with just 2. Okay, what happens next? I'm going to use this particular result now. This line on the denominator is 1 over this, basically. With this is now the whole thing. Here is your z, and here is your w. The r to the a doesn't take part into all of this, so that again is less or equal to 0 to 2 pi r to the power of a. And now on the denominator, I've got the mod of this, mod of r e to the I theta, minus the mod of 1, which is kind of silly to even write it, but let's write so we can match it with the inequality. So that's basically your Z, and this is your W. So, and the inequality from this line to this line. Again, I don't want to waste space for this, but of course, R e to the I theta, modded now. I can mod it individually, okay, with the result we wrote earlier on. And e to the I real is 1. So in fact, this is just merely an R. So I'm going to do that on the next line. So that's equal now from this line to this line. 0 to 2 pi R to the A over just simply R minus 1 d theta. And things fall into place now. This simplifies massively. There's no theta dependence in all of this, so I can actually pull this outside the integral. So it's going to be equal to R to the A over R minus 1, 0 to 2 pi 1 d theta. This integral, of course, is 2 pi. And shall I just do the workings here, or shall I just move to the top? Maybe I should move to the top to allow myself a little bit more space. Let me just write one more line here. I hope it's visible. So that's 2 pi R to the A over R minus 1. And the question now is, that's as simple as I got. And I want to know what happens if R gets very, very large. It goes to infinity, to positive infinity, the radius of the big circle. So I'm expanding this big circle forever. And of course, this line segments will go to infinity from that end. This is of the order, capital O. The 2 pi doesn't take any part in all of this. It's just a constant, and so is the minus 1. So it's of the order of R to the A over R. Okay, and it's very annoying. I have to just rub off just for a very little bit that is left, but let's do it so we do it properly, because I don't know if you can, if the bottom of the board is actually appears in the film in there, so I don't want to be writing stuff that and doesn't show what I'm doing. Okay, so that's equal to the less or equal from all of this order of R to the A minus 1. Rules of indices in there. And what happens now if R gets very large? Well, this power here, because A is between 0 and 1, A minus 1 is in fact a negative power, so it's 1 over basically. So this particular quantity will tend to 0 as R tends to infinity. Okay, so we actually managed to prove that the contribution of around gamma 1 of my f of z as R gets infinitely large actually vanishes. And now I'm halfway. I need to do the same thing for gamma 2. So that was just for the outer circle. I need to do the same thing as I'm shrinking the epsilon to 0. So space again. This time we should be able to do it faster because a lot of the steps here are fairly repetitive. I must say, a lot of these approximations, the first time you see them, they look very, very scary. I remember myself when I first saw a question like this, I thought to myself, no way I can do stuff like that. But after you do a few questions, you realize it's practically the same things, similar estimations, similar kind of stuff. It becomes actually tedious eventually. So we're looking at the gamma 2, that's this one here. So this is going to be parameterized as well. So modulus of, there's my gamma 2, I'll fit it in here. Around the small circle, the z is equal to epsilon e to the I theta. And my dz is equal to I epsilon e to the I theta d theta. And my theta will run, this is running anti-clockwise, sorry, clockwise. So it is actually going from 2 pi to 0. It will not matter in the estimation, but I'll write it the way it appears up there, 2 pi to 0, and you'll see why in a second. So let's put the numbers in, move out of the way so we can see both sides of the board. So this is from 2 pi to 0. My f of z here, so I'm putting in there now on the numerator epsilon e to the I theta to the power of a minus 1. Z plus 1 is epsilon e to the I theta plus 1, chop off that fraction, put the dz is I epsilon e to the I theta d theta. Close bracket, close mod. Tidy. Okay, I'm going to swap the limits to 0 to 2 pi and leave it as it is. Of course, it will generate a minus here, but this is inside the mod, so it hardly matters. It's okay, it's still the same thing, really. I'm going to leave it like that. It's bad karma. I don't like it like this, so I will just swap them. It wouldn't have mattered anyway. I on the top there, I've got an epsilon to the a minus 1. I've got this epsilon there, which I'm going to put together next. I've got the e to the I theta. It's pretty much the same as the previous one. I just want to make sure I don't rush because it's been a very, very long day today and I'm very, very error prone. And the difference is when you are teaching in front of a live audience, of course they'll say, oh sir, you know, you forgot to copy that the next line or whatever, if you're doing some omission or you wrote something the wrong way around or something. Or even if you said sometimes a slip of tongue and you meant different thing but the wrong thing came out, you have a chance to correct it. But here, because obviously I'm recording by myself, if I make a mistake and I don't see it, it's curtains. I mean, this is really bad. Okay, so close mode. So this is now just merely just rewriting this. Okay, tidy this particular quantity. I'm going to now say, use the inequality rather, I don't want to be wasting lines. So the modulus, like I did in the previous one, of the definite integral is less or equal to the definite integral of the modulus of the integrand. So at the moment, all of this is inside a modulus. So it's going to be I'm going to put the two epsilons together, epsilon to the a, e to the I theta, e to the I theta a minus 1, and epsilon e to the I theta plus 1 d theta. So that is we discussed in the previous estimation. And of course, now again, I'm going to use a different color pen and I'm going to do things on the same line. The modulus of a fraction is the modulus of its top over the modulus of its bottom. So I can lose this on there and say that's definitely the same as that. So let's lose the outer things now. They have gone. Of course, we should have copied it again, but it's very, very difficult when you're doing that on a board. And again, property of the modulus. If you have a product, you can take individual moduli, like we did again on the previous estimation. So that's the same as that. We cannot do it again here because of the plus. And let's start seeing what is going to happen in there. First of all, the modulus of I is simply 1. E to the I real modded, again, we explained on the last estimation, is 1. E to the I, again, something real, is of course, again, 1. And so far, we can simplify this expression, make some space again, and it will go to pretty much the same thing that the previous expression went. I think at the very end it's a little bit different, but it's very, very easy. So this is now, I'm going to put less or equal here to maintain the correctness from line to line, because I'll wrap it off. 0 to 2 pi. And this is 1, this is 1, this is 1. This doesn't need the modulus because it's positive. Epsilon is positive, so epsilon to the a is a positive quantity. And we've got again over epsilon e to the I theta plus 1 d theta. Okay, again, the very, very important inequality that I left deliberately on the side of the board here appears again. You must learn a few of these things that I'm doing on this lecture in these estimations, that this particular type of inequality, the e to the I real, which I'm sure you've seen before, the moduli manipulations, is things that do come up often. They're not that hard, and they come in other bits of analysis, I'm sure, which I haven't seen. All right, so this now, again, less or equal, I'm treating that as my Z and this as my W, so I'm looking at this line 1 over, this doesn't take any part of course, is epsilon to the A, and I'm going to have epsilon E to the I theta minus, again let's put this like that to match this particular line. That's my Z, that's my W, that was my Z plus W 1 over, of course, the d theta. And of course, now, again, like in the previous example, epsilon e to the I theta, modded, I can do separate mods for this bit here. E to the I real is 1, so that's simply epsilon. The minus 1 doesn't need, the 1 doesn't need the mod in there, so this line will in fact become in further down as equal now. I forgot the limits there, 2 pi, 0 to 2 pi, 0 to 2 pi, that's my epsilon. That's going to 1 minus 1 over epsilon to the A, d theta. And this again is independent of theta, it's just a constant. So pull it outside, epsilon to the A over epsilon minus 1, integral 0 to 2 pi, 1 d theta. And I think I might be able to squeeze it there rather than rubbing at this stage. So this is a 2 pi, so we got a 2 pi epsilon to the A over epsilon minus 1. So what happens now if we shrink this particular radius of epsilon to 0? What does that produce is the question. Okay, this quantity is much easier than the previous one that we had R. If first of all epsilon goes to 0 on this denominator, the epsilon is not even the dominant term here, so it's the minus 1 that will survive in there. So your denominator, you can think of it as epsilon goes to 0, your denominator is simply minus 1. And of course, here if the epsilon goes to 0, this is a constant, okay? If the epsilon goes to 0 to some power, this numerator will go to 0. So you're going to have a 0 over negative 1. So that definitely goes to 0 as epsilon goes to 0. So that's good news, because that's of course less or equal to 0 if you want in the limiting case. So gamma 2 is goodbye, my friend. So it's all gone. Okay, so these estimations take a long time. And I don't know in exams anymore. I haven't really looked at university exams at all in many years. What kind of things are you expected to show? What kind of workings you're expected to show for something like this? Can you just say evidently? When I was at university, the word evidently was banned from proofs. They take a long time, as I said, the estimation. So let's see what we've done so far. As R tends to infinity and epsilon tends to 0. So this has gone massive, but the important thing is now this straight line segments go from 0 to infinity along the x-axis. Definitely these two things have gone. So what has happened to us? We got now the integral from infinity to 0 of my f of z. Let's write the f of z actually in full form here, which is z to the a minus 1 over z plus 1 dz, plus another one which is from 0 to infinity, 0 to infinity, z to the a minus 1 over z plus 1 dz, and these are these two here, is equal to 2 pi I, I'll leave it as it is in there, I'm not simplifying anything in there, e to the I pi a minus 1. So quite clearly, if I put x's in here because I'm on the x-axis, that should give me my integral. Okay, so I'll just look at this, and all of a sudden I see dark clouds in the horizon. I don't know if you can see what the problem is there. If I say now, because I'm on the x-axis, all the z's are in fact x and my dz is x, so I have x, x, dx, and the same thing on the other one. If I flip this particular integral, so not the integral, the limit, sorry, so I'll put the infinity and the 0 at the bottom, that will generate a minus at the front. And my idea was to say, okay, that's how many of my integrals I've got in there, and then it's equal to that, and come up with an answer. The answer is now scary. This cancel, because if I flip, I got a minus, exactly the same thing, all in x's, and the question is, have I made a mistake in all of my work? So make a lot of mistakes, and I hope this lecture hasn't gone the same way, because now I rubbed off a lot of things, and I'm rubbing even more at the moment. I have to think really hard about what has taken place in here, and what can I do to rectify it. Okay, I might have made a mistake. This actually doesn't worry me. I'm expecting that. It's only because I know what's happened here. Something funny happening there because of the branch cut. But I might have made a mistake. That's not that I haven't made one, because I'm really bad. I just hope I haven't. But this one, let's do a little bit of an analysis to actually see what is going on. What I just said in there, it was at first glance, is not really what is happening in there. So let's see what is going on a little bit. And if we haven't done, I don't know if I've done another branch cut lecture before, I've shown you this. I'll treat it as you see it for the first time. So let's identify which one is which. So the infinity to 0, we're going from the far right to the origin, is the one at the bottom. So this is the bottom one. That's the bottom section along the x-axis, and that's above the branch cut. So it's on the top of the branch cut. Okay, let's look at the top one, because the top one is actually the easier of the two. Normally, with parameterizations along straight line segments, we don't write anything. We just say, listen, if we're on the x-axis, z is equal to x, dz is equal to dx, and that's done. It's not quite strictly speaking true if you have situations with fractional powers and logs, and you have to be very, very careful. You need to be aware of that. And let me explain what is going on a little bit with this. This is the top one. The correct version should be z is not equal to x. That's the actual modulus, if you want, because z is a complex number. That's the modulus, x, e, so if you're on the top, to the 0, I. Okay, so my dz, quite clearly, would have been dx, and that's a constant, e to the 0, I. No problem. Okay, what are these? What is 0, e to the 0, I? E to the 0, I is quite clearly 1. So if you're on the top, you can say z is equal to x for this one. This is also 1, so dz is equal to dx. So you can swap that as well. Does it matter on this one that has a fractional power? Let's have a look. If we go on the fractional power, we can say z to the a minus 1. That's the tricky one that normally causes the problems. You're putting, of course, that is your z, so that's x e to the 0 I, all to the power of a minus 1. So that will become an x to the a minus 1 times e to the 0 I a minus 1. Is that a problem? What is this extra bit? Well, the answer is e to the 0, which of course is 1. So basically, all you're going to put for this particular thing is again x to the a minus 1. So no problem for this particular one. Is it the same for this, however? Let's investigate. Now we are on the section which is underneath the branch cut. So, what is z there? Z is not just x. You have to be very careful. Z is e to the 2 pi I. The argument of this x, if it's running underneath, is 2 pi. Okay, what about the dz? Dz is of course dx. Is this a constant? Of course it is. Just leave it there, to the 2 pi I. So let's look at those two so far. Mod dz, what is e to the 2 pi I? Of course is 1. So this will become a dx again. Will it make a difference if I put now for this z here, if I put x e to the 2 pi I or just x? Well, the answer simply doesn't matter. I can put x because of course again e to the 2 pi I of course is 1. So this again it will be x. We're reaching now the one when things get very, very hairy. Let's look at this numerator, the fractional power. So z to the power of a minus 1. Of course that is my z. X to the e to the, sorry, not next to the x e to the 2 pi I. And this needs to be raised to the power of a minus 1. what is that? Let's write it underneath. X to the a minus 1 times e to the 2 pi I a minus 1. Is that a 1 here? Well, at first glance you might say, yeah, well, yes it is. Well, what's this 2 pi I? It's a multiple. Careful, because this is not an integer. So if it's not a 1, what is it? The answer is we don't know, but certainly it's not a 1 because a has this restriction here, which makes this a non-integer multiple of 2 pi I, and therefore this quantity is what this top needs to be replaced by, and this is not just a straight swap for x to the a minus 1 like it would have been, of course, for this particular one. So this we need to keep in mind. And after we've seen that, this happens when you have logs or if you're having fractional powers. I need to leave that in there because I'm going to replace things in there now. So let's clear the board. So let's create at least room for one more line underneath that. So I need to see this and this at the same time. So first of all, infinity to 0. This numerator now is all of this. So we got x to the a minus 1, e to the 2 pi I, a minus 1 numerator. This, which I put little dots there, is just a straightforward x. So you can write x plus 1 dx for your dz plus the integral from 0 to infinity, and these are all x's, so that's no problem. X plus 1 dx is equal to 2 pi I, exactly the same as I've got there. I'm just copying. All right, so where we can go from there now, of course we need to create our integral, not to infinity. It's there now, but also it will appear there. We need to do a couple of things, so I don't want to waste lines again. We got the limits the wrong way around, so we like the thing to go on the top. So let's put, first of all, I'm writing the minus far away for a reason. So this is now going to be a 0 to infinity. And this extra term that we just got on the numerator is a constant independent of x. So we can actually write it at the front. So I'm gonna rub it off the numerator in a second and write it at the top, so I can see what I've got left. So that has now gone from the numerator. Let's take that off. We don't really need that long fraction line anymore. Let's move the dx a little bit closer as well. So this is my dx. And now it's the final tidy. There's my integral in two places. That's 1, and of course I've got more of this there. So let's put them together. So I've got 1, no plus. Well, I keep writing silly things sometimes. 1 minus e to the 2 pi I a minus 1, lots of my integral, 0 to infinity. Maybe I should have called it capital I or something, so I don't have to keep writing this. It's too late now. X plus 1 dx is equal to this term, which we've been carrying now since we applied the residue theorem in the very beginning. And I just hope now, after all of this, there's no mistakes there and everything works, because all it takes is to miss a factor of 2 or something very silly, and the thing doesn't quite work, and then all of this, and it's going to be a very long lecture, goes down the drain, because of course we can't just trace our mistakes because we rubbed it off. All right, so that's infinity there. So we got the integral from 0 to infinity, x to the a minus 1 over x plus 1 dx is equal to that divided by that. So that is 2 pi I times e to the I pi a minus 1 over 1 minus e to the 2 pi I a minus 1. And I need to show that this is in fact that quantity up there. I think I can see what I need to do. those who are doing further maths in some boards and in some modules, and the complex numbers, further maths, ordinary further maths, if you have to sometimes complex series that they involve normally geometric progressions of exponentials, and you normally, I don't know if you remember or if you start seeing these things like that, you write it as a C plus IS, and you get a convergence series for that and a convergence series for that. You get expressions which look something like that in your workings. So those who have seen this kind of stuff, they should be able to actually see what needs doing in there. Otherwise, it can be quite tricky to manipulate it. So here is we're going to create a shine at the bottom by factorizing a quantity, and the shine of a complex quantity will go into a sign eventually, and everything should hopefully cancel. So if we write it as follows: factorize e to the pi I a minus 1 on your denominator. So this requires the negative exponent of that, so minus pi I a minus 1, so that gives you your 1 minus, we're only going to have now a pi I a minus 1, extra long fraction, and on the top we got 2 pi I times e to the I pi. I don't know why I wrote I pi there and pi I there. I suppose do strange things sometimes. Okay, this is all correct, I like to think. Just taking last minute just in case I make a mistake. So I'm getting very tired now. Looking forward to go and eat. Okay, this will cancel that, so that's exactly the same. And this particular one, I want to factorize a minus outside this bracket. So if I factorize a minus there, it will create a minus there and a plus in there. And because I don't want to lose that minus, I'm going to put it on the top. So I'm going to have negative 2 pi I on the next line. This is this minus here that I put on the top, and the bottom doesn't the bracket. Now I'm going to write it back to front with the positive item first. Is e to the I pi, I'm going to write as I pi, it's very bizarre, pi I pi a minus 1 minus e to the minus I pi a minus 1. Now what is that? That's of course the shine, actually two lots, because normally I would have had to have halves in there. Okay, so I have two lots on the bottom of the shine. And what's in the argument of the shine? The argument of the shine is I pi a minus 1 and the minus 2 pi I on the top. Next, of course, is the obvious property, shine of I real is the same as I sine of real. So that's from further maths, is not actually university stuff. 2 pi I negative, and this is now 2I, and the shine becomes a sine of exactly the same argument. And because I know what I'm going to do next, I'm going to, after I take the I out from the shine and it becomes a sine, I'm going to multiply this bracket pi a minus pi. And I think we're home dry now. What happens in there? First of all, the 2's cancel. The i's cancel, which is good because now this becomes real. And we got a minus pi on the top. So we got the pi that we need up there. You have to lose the minus, and I'm sure it will work. Otherwise, we have by minus. I will cry. And now this compound angle. So this is going to be a sine pi a cos pi minus sine, no sine, minus cos, beg your pardon, minus cos pi a sine pi. So that's the compound angle of sine a minus b here. And yes, it does work because of course this is 0, the sine of pi is 0, so it kills that. And the cos of pi is of course minus 1, and this will be now minus pi over minus sine pi a, and of course the minus now disappears, and the required answer has been achieved. A very lengthy lecture. I hope you followed it. I hope you enjoyed it. I'm gonna go and get something to eat. And who's laughing now? I'll see you soon.